So let us prove the following proposition about cyclic groups. So let G be a cyclic group, and suppose that the little x is a generator of G. Then I claim this equality. What does this equality mean? How do we read it? This is the order of the group G. So this is saying the number of elements in the group G is equal to the order of the element x. Remember, the order of an element is the smallest positive integer such that the smallest positive power that brings that element to equal identity. More specifically, okay, so this is, let's just kill this completely. If G is finite and has n elements, then the nth power of the generator is 1. And these elements, e, x, x squared, all the way to x to the n minus 1, are never equal to one another. So are all distinct elements of G. On the other hand, if G is an infinite cyclic group, then x to the n is never equal to 1. Sorry, it's never equal to e. Both of these should be e's. Is never equal to e. Except when n is 0, of course, then by definition it's equal to e. But when n isn't 0, then x to the n is not equal to e. And if a is not equal to b, then x to the a is not equal to x to the b. Okay? So if I take a generator and I look at x to the 17th and x to the minus 321st, I know these are different elements. I don't need to check anything. So let's prove this proposition. So let's first consider assume that the order of x is n. And it's finite. Okay? So I'm saying G is a cyclic group which has a generator whose order is finite. And suppose the order is equal to n. Then the elements e, x, x squared, all the way to xn minus 1 are all distinct. Why is that? Because if two of them were the same, for some, okay, so that means some of these, right? If I say that some of these are the same, that a and b then means are between 0, 0th power, and n minus 1st power. And of course, without loss of generality, I can assume that a is less than or equal to b. So for some, a less than or equal to b, less than or equal than n minus 1. Then what do I know? Then x to the b minus a, so if I multiply them, say, both sides by x to the minus a, so I get, right, x to the minus a, so then I get e on this side, if I multiply it by x to the minus a, and here I get x to the b, x to the minus a, but that's just x to the b minus a, as we discussed in one of the previous videos. What do I know about b minus a? Well, look, a and b both sit between 0 and n minus 1, so their difference is less than n. And b minus a is less than n. Right? Because b is greater than or equal to a, I know that it's greater than or equal to 0, but it's also less than n, because the furthest apart they could possibly be is when a is 0 and b is n minus 1, and then the difference is n minus 1. Oh, but that can't be, because that then would be a... oh, sorry, but I actually want to assume they're not the same, right? Well, if they're the same, then they're of course, then these two are of course equal. So assume they're not the same, so a is actually less than b. So here I get that it's actually bigger than 0. Okay, so b minus a is bigger than 0 and then less than n. But this cannot be, because then b minus a is a smaller positive integer such that x to that integer gives me the identity. Smaller than n, and n is the order of x, so n is the smallest such. So let's see how the sentence goes. Then the elements are all distinct because if that happens for some a and b like this, then this happens, which contradicts the minimality of n, which contradicts the minimality of n. Once again, n is the order of x, so n is the smallest positive integer such that x to the n is equal to the identity. However, if x to the a is equal to x to the b, for some a and b between 0 and n minus 1, and a not being equal to b, then I have this. Then I get that x to the b minus a is equal to e, and b minus a is strictly bigger than 0 because b is strictly bigger than a, and strictly less than n because the furthest they can be apart is a being 0, b being n minus 1. So that gives me an integer that is strictly smaller than n. So when I raise x to that integer, I get the identity. That contradicts the fact that n was the order. Okay, so I know that if n is the order of x, and so it's finite, then these elements are actually all distinct. Okay, so what does this mean? So G has at least n elements. Oh, how do I know that? Well, just count. They're all distinct. They all lie in G. 1, 2, 3, n, right? This is the first one, so power 0. Second one, so power 1. Third one, so power 3. Nth one, because that's power n minus 1. So I have at least n elements in G. So the order of G is greater than or equal to n. Okay, let's continue with this proof. Now consider x to the t for some t in z. So I'm taking this x, still working under this assumption, taking this x and raising it to some arbitrary power in z, not just one of those between 0 and n minus 1. So then, using the division property, look how this all comes together. For z, this is some of the things we talked about at the beginning of the semester. I can write t as q n plus r, with q and r being integers, but r strictly between 0 and n. Note that n is not 0, of course, right? So, yeah, assuming that n is the order of x, the order cannot be 0. The order is the smallest positive number. Okay, well then, let's look at this x to the t. That's x to the qn plus r. So that's x to the n to the q times x to the r. And what's x to the n? Well, n is the order of x, so that's just the identity. So that's e to the q, x to the r. But the identity to any power is the identity, so that's e x to the r. So that's x to the r. Ah, okay. So x to an arbitrary integer gave me x to the r, where r is between 0 and n. So that means that thing is one of those. One of those, yeah? So that means it belongs to the set e x squared x to the n minus 1. I don't know which one it is. It depends on the remainder r, but it's just one of those. So every power of x is one of these elements here. Thus, the order of g is less than or equal to n. How do I know that? Okay, so g is cyclic. That's our assumption. And x is the generator of g. So every element in g is a power of x. I took an arbitrary power of x here. Arbitrary. T was completely arbitrary. And what did I get? That this arbitrary power of x is one of these guys. So every power of x is one of these guys. But every element of g is a power of x. So every element of g is one of these guys, and there are only n of them. So that means the order of g is at most n. Collecting these two together gives me that g, the order of g is n. So what did we show? We've shown that if g is cyclic and it has a generator whose order is n, then g itself has exactly n elements. Okay, so let's continue. So that's all that worked under the assumption that the order of x is finite. So now assume that, now let's suppose that the order is actually infinite. Now suppose. So let's do the complementary case. The order of x is infinite. I.e., no positive power of x is equal to no positive power of x equals e. Right? Because if some positive power of x equals e, then that means the order is finite. There's a smallest such, so the order will be finite. If the order is infinite, that means no positive power of x equals the identity. So if x to the a is equal to x to the b, again for some a less than b, can assume without loss of generality that, so I mean a not equal to b, but I can assume without loss of generality that means that a is less than b. Then as before, then x to the b minus a is the identity. Oh, but b minus a is a positive integer. And I just said there's no such thing, which contradicts. Which contradicts the order of x being infinite. So what's the conclusion? So the elements, well, I don't know, x to the minus 3, x to the minus 2, x to the minus 1, e, x squared, x cubed, x to the 4th, and so on. These are all distinct elements. Are all distinct. So i.e. x to the a can equal x to the b only if, in fact if and only if, a is equal to the b. A is equal to b. So that means when a isn't b, I get different elements. How many different a's and b's do I have? Well, infinitely many, right? A and b can be any integer. So that means, g has infinitely many elements. So in this case, we get that g is infinite. All right. So when g has a generator whose order is finite, then g is finite. If g has a generator whose order is infinite, then g is infinite. So now I also know the converse of these. If g is a finite cyclic group, then it must have a generator whose order is finite. Because if it had a generator whose order is infinite, then G would be infinite. And vice versa, if G has a generator whose order is infinite, then G itself must be infinite. Because if G were finite, it would have, if G is infinite, then it must have a generator whose order is infinite. Because if it had a generator whose order was finite, then G would be finite. Okay? So we get the implications now we got in the proposition. If G is a finite cyclic group, then it has a generator whose order is finite, and in fact, then I know the order of this generator. If it's equal to n, then I know the group also has order n. So that means the order of the group is equal to the order of the generator. And I know that e, x, x squared, all the way up to x to the n minus 1 are distinct elements of G. On the other hand, if G is infinite, then I know the order of the generator is infinite. So again, the order of the group is equal to the order of the generator. And then any power, different powers of x give me different elements. So all these guys are actually different. Okay, so this proves our proposition.